Welcome to my channel. In this video, I will explain how to write the laboratory manual for verification of mesh and nodal analysis for an AC circuit. So, before discussing about how to write the laboratory manual to verify mesh and nodal analysis for an AC circuit, let us see how to write the manual in the observation. So, if any BTech student is watching this video, so it will be useful to them. So in this slide you can see here. So this is the right side page of your observation. This is the left side page. So in the right side page you must write the title, date and experiment number, and you must write the aim, apparatus required, theory, procedure, formulae, calculations, theoretical proof, practical proof, precautions and results. Only on the right side pages in your observation. On the left side pages you must draw the circuit diagrams, observation tables. If model graphs are available, you must draw the model graphs. So for this experiment, model graphs are not there. Okay, so this slide is in general for all the laboratory experiments of electrical engineering. So now let us go to our experiment. So the title of our experiment is Verification of Mesh and Nodal Analysis for an AC Circuit. So you can pause the video and you can copy the title in your notes if you are a BTech student. If you are noting down this content in your notes, you just pause the video to copy the content from this video. So the aim of the experiment is, here we are going to verify mesh and nodal analysis. We are going to verify mesh and nodal analysis using both hardware and MATLAB software. That's why aim has been divided into two parts. In the first part, to verify mesh and nodal analysis for the given AC circuit using hardware is our aim. In the second part, to verify mesh and nodal analysis for the given AC circuit using MATLAB software is our second part. So let us see the apparatus required. So for doing the hardware experiment, the apparatus required are a single phase auto transformer whose range is 230 by 0 to 270 volts, and quantity required is 1. We need a circuit board. The quantity required is 1. We need an ammeter of 0 to 50 milliamperes, and type moving iron type ammeter we need, that is MI type, and the number of ammeters required to do this experiment are 3. For the circuit that I have chosen to do this experiment, for that particular circuit we need 3 ammeters, and we need voltmeter of range 0 to 30 volts, moving iron type, and number of voltmeters required here to do this experiment are 6. For the circuit that I have chosen, for that circuit you need 6 voltmeters, and you need a decayed inductance box 1, quantity 1, connecting wires. It depends on the circuit that you have chosen to do the experiment. The number of connecting wires may vary, so that's why the quantity required is required number. So you must always draw the tabular column to write the apparatus required to do the experiment. You can pause the video and copy this in your notes. So for doing the software experiment, we require only MATLAB software. So software required is MATLAB. So let us see the circuit diagram. So for doing the hardware experiment, so here we are going to give the single phase AC supply of 230 volts 50 hertz. Okay. So it is single phase AC supply is given to the single phase auto transformer here, whose range is 230 by 0 to 270 volts. And this is our double pole single throw switch. So when this double pole single throw switch is closed, the supply will be given to this dimmerstat, that is single phase auto transformer. Single phase auto transformer is also known as dimmerstat. So across this single phase auto transformer, and voltmeter is connected of 0 to 230 volts moving iron type, and in series to this resistance R1 of 47 ohms. An ammeter of 0 to 50 milliamperes moving iron type is connected. In series to 2000 ohms, an ammeter of 0 to 50 milliamperes Mi type is connected. And in series to R3, R4 and inductance L, an ammeter of 0 to 50 milliamperes Mi type is connected. So ammeters are connected to measure the current flow in each branch. And so this circuit is for the nodal analysis. You can pause the video. Okay. And copy down. So by nodal analysis, we will verify Kirchhoff's current law. So here we want to verify the Kirchhoff's current law. So the algebraic sum of all the currents meeting at a junction must be equal to 0. So this is our node here. At this junction, the currents, all the currents entering, algebraic sum of all the currents entering and leaving should be equal to 0. So that's why we have connected ammeter in this branch, and this branch. Now for mesh analysis, this is our circuit. So here also same, we are going to take an AC supply. These are the terminals of AC supply, single phase terminals, phase and neutral. P means phase, N means neutral. Single phase 230 volts 50 hertz AC voltage source is connected here. And this source is connected to this single phase auto transformer of 230 by 0 to 270 volts with the okay, it is connected to it through a switch, which is a double pole single throw switch, and an voltmeter of 0 to 30 volts moving iron type is connected across the output terminals of your auto transformer. Across 47 ohms, a voltmeter of 0 to 30 volts moving iron type is connected. Across 510 ohms, a voltmeter of 0 to 30 volts moving iron type is connected. Across 2000 ohms, at 0 to 30 volts moving iron type voltmeter is connected. Across 510 ohms, 0 to 30 volts moving iron type voltmeter is connected. Across this inductor of 0 to 0.05 Henry, and voltmeter of 0 to 30 volts moving iron type is connected. So here if you observe, there are two loops. This is one loop, this is one loop. So in mesh analysis, we will verify Kirchhoff's voltage law. So in each loop, the algebraic sum of voltages must be equal to 0. So in this loop, algebraic sum of voltages must be equal to 0, and this loop also algebraic sum of voltages must be equal to 0. So you can pause the video and you can copy down this circuit in your notes. So for software experiment, for nodal analysis, I have taken the same circuit. So you have to take an AC voltage source, and you need a voltage measurement, and you need a continuous RMS block and a display. And since it is nodal analysis, we are going to connect current measurement across each and every element in each branch. So you can see here R1 of 47 ohms to in series to it, a current measurement, this is current measurement, is connected, and to it and this current measurement, one of the terminals, of course it is connected to the circuit, another terminal, output terminal, this is here, this is plus, this is I, this is minus. Okay, I will just write it down so that it will be more easy to understand. This is plus, okay, this is I, and this is minus, sorry. This is minus. Similarly, for this ammeter is all, for this ammeter, this is plus, this is I, and this is minus. For this ammeter, this is plus, this is I, and this is minus. Okay, so the I terminal of this current measurement, okay, these are current measurements. Okay, so for hardware experiment, we call them ammeters to measure the current. Here, they are the current measurements. So in this current measurement, the I terminal must be connected to continuous RMS, and to the continuous RMS display should be connected. And the I terminal of this current measurement, which is in series to this 2000 ohms continuous RMS, must be connected, and to this display should be connected. And in this R3, R4 and L, they are in series to them current measurement should be connected, and I terminal of this current measurement should be connected to continuous RMS. To this we will connect a display. So here we are going to verify Kirchhoff's current law. Therefore, current entering at this junction must be equal to current leaving this junction. So I have taken an add here, add block, and I have added all the currents here. So the display should show 0. You can pause the video, and you can note down, you can draw the circuit diagram in your observation. Next, for mesh analysis. So this is our circuit. This is AC voltage source. Across AC voltage source, a voltage measurement is connected to the voltage measurement V terminal. Continuous RMS is connected to the continuous RMS. Display should be connected. Similarly, across 47 ohms, voltage measurement is connected to the V terminal of voltage measurement. Continuous RMS block must be connected, and it should be given to the display. And similarly, across 2000 ohms, a voltage measurement should be connected, and continuous RMS should be connected to the V terminal, and the output terminal of continuous RMS must be connected to the display. Similarly, across 510 ohms resistor, voltage measurement is connected, output terminal of voltage measurement is connected to continuous RMS is connected to the display. Similarly, 510 ohms resistor, across it voltage measurement must be connected, output terminal of voltage measurement should be connected to continuous RMS must be connected to the display. Across the inductance of 0 to 0.05 Henry, voltage measurement should be connected. Across output terminal of the voltage measurement should be connected to continuous RMS should be connected to the display. Okay. Now this voltages that have been measured in each loop, they are being added here, and an display is connected here, so that the algebraic sum of all voltages must be 0 in each loop. So for this loop, the algebraic sum of here, this display should show 0. Similarly, what I have done here is, this is a resistor, this is a resistor. Both the voltage across these two resistors, this 510 ohms and this 510 ohms resistor, both the voltages I have added here. Okay, and whatever after adding those voltages, what is the voltage value that can be shown in this display? Okay, okay, I have taken the square of that resistance, and here inductance value, square of the, not square of the resistance, square of the voltage that has been measured here, which is obtained by adding the voltages across each resistor. So that voltage square is taken here. Similarly, the voltage across the inductor, that voltage square is taken here. Okay, so after taking the square, those two voltages are added and square root is taken here. So we are going to square root it. Okay, and we will see the voltage value here. So now this voltage is added with this voltage across this element. So that is it. It is added here, and the display should show 0. So this display 6 here, it should show 0, and this display 7, it should also show 0 while doing the experiment. You can pause this video. So here this is plus, this is minus, this is minus, and this is also, this is plus, these two are plus symbols, and here this is also plus. Okay, here this is plus, and this is minus. So you can pause the video and you can copy down this circuit diagram in your notes. So in these two loops, this is our loop 1. So I can't write. Now let us see the observation table for mesh analysis. For mesh analysis, to verify Kirchhoff's voltage law in mesh analysis. So theoretical values, we have to do the experiment. We have to write down theoretical value, source voltage value, voltage across R1, voltage across R2, voltage across R3, voltage across R4, and voltage across the inductor. Okay. So you must theoretically we must calculate, you must tabulate it in this tabular column, and after doing hardware experiment you must note down all these values in this tabular column. After doing software experiment we have to note down all these values. So actually, yeah, we can write down the values. So we have connected displays across each and every element in the software experiment. So you will get the values, you can note it down here. For nodal analysis, this is the tabular column. So theoretical values, hardware experiment values, and software experiment values. You need source voltage value, current IR1, current IR2, and current IR3. Actually, IR3, R3, R4, and L are connected in series. So current IR3 will be equal to IR4 equal to IL. Okay, so you have to calculate the the currents theoretically, and you must tabulate in this column. And source voltage, of course, it is already specified, you just write it down. And after doing hardware experiment you must write down these values in this tabular column. After doing software experiments you must write down all these values in this tabular column. You can pause the video and copy down this table in your notes. Now you have to write the theory of at least one page in your notes. You have to, if students are going through this video, they can refer to some textbook, and from the textbook they must write the theory. Now let us see the procedure for hardware experiment. Connections are made as per the circuit diagram. Switch on the AC supply and vary the single phase auto transformer. Apply RMS voltage of 20 volts to the circuit by switching on the supply. Note down the ammeter and voltmeter readings in the tabular column, and calculate the algebraic sum of voltmeter reading values in each mesh to verify the algebraic sum of the phasor voltage drops around a mesh is 0. You can pause the video and copy down this in your notes. One more step, calculate the algebraic sum of ammeter readings values at each node to verify the algebraic sum of nodal currents at each node is 0. So this procedure is in general for both nodal analysis and mesh analysis. So for software experiment, procedure is enter the command window of MATLAB, create a new model by selecting file, later select new, and later select model. So pick up the blocks from the Simulink library browser and copy them in the new model, and connect the blocks as per the circuit diagram. Set the source voltage and parameter values as per the circuit diagram, and debug and run the circuit. pause this video and copy down the procedure. So note down the voltage measurement and current measurement values in the tabular column. Verify the algebraic sum of phasor voltage drops around a mesh is 0, and verify the algebraic sum of node currents at each node is 0. Now you have to do the theoretical calculations for the given circuit. So leave at least 2 pages in your observation. If you are a BTech students, leave at least 2 pages in your observation to do the calculations. Next, leave at least half a page for the theoretical proof to verify Kirchhoff's voltage law for mesh analysis and to verify Kirchhoff's current law for nodal analysis. Theoretically, whatever calculations that you have done, for that you have to do the theoretical, you have to verify that. So that's our theoretical proof. Similarly, practical proof, whatever hardware experiment that you have done, for that verify Kirchhoff's voltage law for mesh analysis, Kirchhoff's current law for nodal analysis. So leave at least half a page for practical proof. And let us see the precautions. Initially keep the thermostat at 0 output position and avoid loose connections, avoid short circuit of thermostat output terminals. And at last write the result. So the result is Kirchhoff's voltage law in each loop has been verified by mesh analysis, and Kirchhoff's current law at each node has been verified by nodal analysis, both for hardware experiment and hardware circuit and using MATLAB software. Thank you for watching the video. If any suggestions are there, you can mention in the comment section. If you like this video, just click on the like button so that this video will be available, or this video can reach to many people. Thank you.